Alright boys and girls, welcome back. I'm Daniel for Rock the JVM, and this video is part 3 of type level programming in Scala. Now this mini-series is pretty tough, so you're supposed to be a very comfortable Scala user, and in particular with implicits and type aliases, because we're going to use them a lot in this video and in the other parts of the series, which by the way I really recommend you watch. So it's highly recommended that you watch parts 1 and 2 before diving into this video, because we're going to use what we created in those videos here as well. Of course, I will recommend that you code alongside me, and whenever you need to refresh your memory on these kinds of concepts, just return to this video or to its written form at rockthejvm.com/blog, and you will find the links to everything, including the articles and the first 2 parts, in the description. So without further ado, let's get back to our code and let's continue where we left off. So this whole mini-series is about using the power of the Scala compiler to enforce complex relationships between types that mean something to us. And in the first part, we introduced the concept of a natural number as a type, and we defined numbers in terms of their succession. So for example, the number 2 is the successor of 1, number 3 is the successor of 2, and so on and so forth. And by this, we can represent the entire natural set. Now, in the first part, we defined the less than relationship between numbers as types, and in the second part, we learned to add 2 numbers as types. Everything happens at compile time. So I'll highly recommend that you watch the first 2 parts in this mini-series to understand what we've done here and the kind of approach that we followed, so that the compiler can prove the certain relationships between types at compile time before our program runs. Now, the third time is the charm, and in this third part, we're going to do something really magical. So we're going to rely on the first 2 parts to sort lists at compile time. All right. Now, I mentioned earlier in the previous, in the first part, that I'm using Scala 2, and I'll update this series once the Scala 3 version arrives. So you'll need to add the Scala lang %Scala reflect package in your build.sbt. So add this to your library dependencies if you haven't done so already. Now, in my type level programming application, I've imported Scala reflect to runtime universe, and I've added this show method, which takes a value of type t and an implicit type tag, which the compiler automatically builds for you, so that you can write the content of a type at runtime. So we are simply printing types at runtime, and we're carrying out some information to the runtime so that we can see what the compiler has inferred for us, but in no way is this a cheat. So everything that we're going to write relies on compile time, and we're going to only print the results at runtime with this show method. All right, so let's carry on, and we're going to do a merge sort algorithm with lists. So first of all, we will need to define what a list is, and we will define a list as a type, not as a value, via a trait that I'm going to call HList. And the name comes from heterogeneous list, and this HList has, I'm going to define that as a class HNil, which extends HList. So notice that the empty list is represented as a type. And I'm also going to represent the type cons, or a prepend. All right, so I'm going to use the familiar colon notation here. And this takes 2 type arguments, a head, which is a natural, and we define the trait natural at the very top. So this is the representation of natural numbers. So basically this is a number, and the tail, which is an HList. And this extends HList. Okay, so in the same style as we defined the nil case class and the cons case class, we are defining the nil and cons as types themselves. All right, so the cons type takes 2 type arguments, the head, which is a natural, and tail, which is a list. Now, you may have seen several similar definitions for this kind of heterogeneous lists in shapeless or other libraries. And in our case, the HList is restricted to nat types, so in the natural numbers. Now, we're going to sort these HLists using a merge sort algorithm. And you're probably familiar with merge sort, and if you want to sort a list with this kind of algorithm, you will need to do 3 major operations. You need to split the list in half, you will need to sort the lists, or sort the halves, and then merge them back. in sorted order, that is. So after you sort the halves, you will need to merge them in sorted order. And we will implement these three operations in turn, starting with the split. So we will need to be able to split a list exactly half, or at most one element difference, if a list has an odd number of elements. Now, I bet you're used to encoding operations and types from the previous parts, so I'm going to encode the sort operation in a similar fashion. I'm going to define a trait, then I'm going to call split, and this trait has three type arguments. HL, that is an H list, and for brevity, I'm just going to consider this a list. I'm not going to use any Scala standard library lists. So when I write H list, I'm going to say this is simply a list. So HL is a list, and L is a list, and R, which is a list. And what do I mean by that? This split trait says that this HL list was split into left and right, and both of these are H lists themselves. Now, as before, we're going to make the compiler infer the instances of split for which this HL is split into L and R, as I'm going to show you shortly. And if you are familiar with the pattern that we followed in parts 1 and 2, we define those as implicit values and methods in the companion object of split. So I'm going to define the companion object for split, and I'm going to start with an implicit val that I'm going to call basic. And the basic comes from the first axiom of splitting a list, which is the fact that an empty list will always split into empty and empty. That is, there is an instance of split of h-nil, h-nil, and h-nil. So the compiler can automatically use that to compute other implicits. So I'm going to type that as split h-nil, h-nil, and h-nil. And I'm going to simply construct an instance of this type. So I'm going to say new split of h-nil, h-nil, and h-nil with no content. All right, so this is the first axiom of splitting a list. Now, the other axiom is the fact that whenever you split a list of a single element, that same list will be the left-hand side of the result. So if I define an implicit def, I'm going to call this basic2, and I'm going to do proper spelling here, that takes a type argument. I'm going to call this n from a natural number. And this basic2 will always create a split in which the original list is that number n concatenated with h-nil. So we can use this colon type as an infix type here. So this is colon of n and h-nil, but I hope this is more readable. And this original list will be split into itself and nil on the right hand side. So this is a single element list, and I'm going to simply construct a split of n concatenated with h-nil, n concatenated with h-nil, and h-nil with no implementation. So these are the two essential operations that the compiler will rely on to build whatever split instance that we might need. Now, the general, most interesting, and most difficult case is the inductive one, when you have a list with at least two elements that you will need to split. And so I'm going to define an implicit def. I'm going to name this inductive, and I'm going to add multiple type arguments here. I'm going to add at least two natural numbers. So I'm going to say n1, which is an at, n2, which is an at, and we will need some additional type arguments for the tail, which is an h-list, and the left and right, which that tail is split into. So I'm going to say L, which is an h-list, and right, which is an h-list. And I'm going to require that this method take an implicit split, which is of type split of tail with left and right. So if the compiler has access to an instance of split where the tail is being split into left and right, then these two natural numbers will be distributed in between left and right. So n1 will go to L and n2 will go to R. And the end result is going to be of type split, where the original list is n1, n2, and tail. So this is the big list that we're going to split. And because the compiler can automatically create or have access to a split of tail left and right, N1 will go to L and N2 will go to R. So I'm going to say N1 with L and N2 with R. And at the very end, I'm going to simply say new this thing. So you new split, and I'm going to copy the type argument. And I'm going to simply pass no implementation. Now, this particular method is very hard to read. So it has 5 type arguments and an implicit parameter, and the end result is a little bit hard to read. So if the compiler can have access to an implicit instance where the tail was split into left and right, so the presence of this split instance means to us that the tail was split into left and right, then this list, N1 and 2 tail, can be split into N1 with L and N2 with R. And the compiler can automatically create an instance of this split for us. So the presence of an instance of split of a certain type means to us that an HL was split into L and R. And this is what this inductive method does. And I'm going to pass some examples, and I'm going to show you how it works in a second. Now, given all these axioms over here as implicit vals and defs, we can then prove the existence of a split of any kind of combination here, and we're going to show which ones are valid and which ones are not due to the compiler figuring out which implicits it can construct and which it cannot. And I'm going to add an apply method here in the split companion object, so I'm going to define apply, which takes 3 type arguments, HL, which is a list, a left, which is a list, and a right, which is a list. And this returns whatever implicit the compiler can find of a split of HL, L, and R. And I'm going to simply use split. So this apply method kind of works like implicitly because it fetches whatever implicit the compiler can have in scope and returns that to the user to do something with it, all right? And we're going to call this apply method to show you how the code can compile, all right? So let's test it out. I'm going to define a valid split as a split, and I'm going to pass a list here, _1, _2, _3, h nil. So this is a list of 3 elements with air quotes. So this is the type that represents a list of 3 natural numbers. And the left hand side should be 1 and 2. So I'm going to 1 and 3 actually. So 1 goes to the left, 2 goes to the right, and 3 goes to the left. So I'm going to say _1, _3 h nil, and _2 h nil. So on the right hand side, I'm going to say split.apply with no type arguments because the compiler can figure them out from the declaration of this value. And in this case, if the code can compile, then the compiler can find an implicit split of this type. And I'm going to show you how the compiler figures that out. And to do that, I'm going to use a keyboard shortcut that you can also find in IntelliJ. I'm on a Mac, I can press Ctrl-Option-Shift+ to show implicit hints here. If you're on Windows, you can do Ctrl-Alt-Shift+, if I remember correctly. So notice here what kind of implicit value the compiler can automatically infer for us. It runs the inductive with basic 2 with a particular type argument, which is, I think, _3. So let's break this down. The compiler requires an implicit split of this particular type. So the compiler says, I require an implicit this thing so that I can return it from the apply method. Now, how can I build an implicit of this type? Well, I'm going to call the inductive method with the following types. N1 is the number 1, N2 is the number 2, and tail is the rest, _3, ::nil. So I'm going to say _1, _2, _3 with nil. And because the required return type is N1 with L and N2 with are, you can match these against the required types in the implicit. So n1 with L, so L must be this thing, _3 with nil, and R with me must be the number 2 with nil, which is nil here. All right, so L must be the number 3 with nothing, and R must be nothing. So because the compiler needs to run this inductive method, it will require an implicit split of TLR, and tail is _3 with nil, and the left and right must be exactly this. So I'm going to say _3 with nil, and right must be nil. Now, how can the compiler build such an instance? Well, it can build such an instance by running basic2 with the number _3. So I'm going to say _3 here. And this will build a split of this exact type. So by running basic2 with _3, the compiler can build an instance of split where the list of _3 is split into itself and nothing, which can then inform the creation of the other implicits backwards. So notice how the dependent implicits are organized so that the compiler can build the big implicit that we want in the apply method. So this is what this implicit hint will also show you. Split.apply will run inductive with basic2 with _3 as the type argument. And so the compiler can automatically build an implicit of this type, and because it can, then it proves that the list 1, 2, 3 can be split into 1, 3, and 2. All right, so we're going to be using such implicit instances for the compiler to prove that a list can be split into whatever L and right we supply. All right, so this is how we can split a heterogeneous list in this sense, by using these basic axioms and the inductive axiom, which is a little bit hard to read, but with a little bit of practice, you'll start to see how the compiler builds instances as proofs for you. Good, so we are done with split. Now, we need to be able to merge two sorted lists back, and then we will go to sort a list by requiring that the halves be sorted as well. So we are going to move to part 2 of this video, which is merging sorted lists into a sorted list. Now, you know the drill. We're going to follow the exact same pattern, and we'll create a new type which will have the meaning of a sorted merge of two lists. So I'm going to define a trait that I'm going to call merge, and this takes two lists and a third result list. So I'm going to say LA, which is a list, LB, which is a list, and L, which I'm going to call the result list, which is an H list itself. So this means that LA merges with LB and results into the final list L. So if the compiler can find an instance of merge where the types are LA and B and L, then it means to us that LA merged with LB results in L. Right? So this is how we would read a type like this. Now, we will start as always by defining a companion object for merge, and we are going to define some basic implicit vows or defs. In our case, we will define two basic implicit defs to signify the fact that a list merged with an empty list results in that list. And we will define two implicit defs for it, and I'm going to explain why. So I'm going to define an implicit def, which I'm going to call basic left, which takes a list as an H list. And this will always construct a merge where the left-hand side is H nil, that list L, and the result will be L. And I'm going to construct that for us. So new merge with H nil, L, and L with no implementation. So this means that the compiler can automatically build a merge where H nil merged with L results in L. So this is how we would read this type. And I'm also going to define an additional method that I'm going to call basic right. And this will construct a merge with L and H nil. And I'm going to put the right types here. And that is because to the compiler, a merge with h-nil, L, and L is different from merge with L, h-nil, and L. So you have these types right below one another, you know they are different. And so we will be able to build an instance of merge where h-nil plus L equals L and L plus h-nil equals L the other way around. Now, the inductive implicits are going to be pretty interesting because we need to consider two lists that have each an element at least. So otherwise, if you have a list which is empty, then this will be covered in one of these two basic axioms. So we will require two lists. Let's call this L1, which is, let's say, N1 with T1. So this number 1 prepended to some sort of tail. This might be empty, it might not. And L2, which is N2 with T2. So we want to merge these two lists. Now, obviously, if you want to merge two lists, you will need to compare their heads. So if N1 is less than N2, then the end result is going to be N1 prepended to, I'm going to put some curly braces here, and I'm going to put 3 dots here to signify that this will be whatever is left from merging T1 with this other list. Okay, so if you want to merge L1 and L2, and the first element of the first list is less than the first element of the second list, then this one has to stay at the front of the result, which is what I'm doing here. And the result is going to be whatever is left from merging the tail with the other list. Otherwise, if you have N2 less than or equal to N1, then you have N2 at the front of the list, which you obtain after merging the first list with T2, because N2 stays at the front. So we will need to embed these two conditions as separate implicit defs. And I'm going to define an implicit def that I'm going to call inductive LTE, that is less than or equal. And this will take several type arguments. I'm going to have N1, which is a natural. You have tail1, which is a list. Then you have N2, which is a natural, and tail2, which is a list. And I'm also have what I'm going to call an intermediate result, which is an H list as well. So this IR part is an intermediate result. And this requires the presence of an implicit merge, which is of type merge of the following. And I'm going to consider this inductive LT case by putting the less than or equal sign here just to make it easier. So if N1 is less than or equal to N2, then I will require the merge of tail1 and the other list into colon T2. So I'm going to have an implicit merge of tail1, that is the left-hand side. The LB is going to be N2 with T2, so the same original list, and the intermediate result. So I will ask the compiler to figure out if there is a merge of this type, and also I'm going to ask for an LTE implicit instance of type less than, between, or less than or equal, so less than or equal between N1 and N2. So if the compiler can find an implicit instance of merge where T1 plus the other list goes to the intermediate result and N1 is less than or equal to N2, then the compiler can automatically build an instance of merge where the original lists are L1 and L2, that is N1 with T1 and N2 T2, where the final result is going to be N1 prepended to the intermediate result. So I'm going to say N1 prepended to intermediate result. And in terms of implementation, I'm going to copy this type and I'm going to instantiate it with no implementation. So if the compiler can merge T1 with N2 with T2 in this intermediate result and N1 is less than or equal to N2, then the compiler can automatically build an instance of the first list merged with the second list in which the result is N1 prepended to this intermediate result. Okay, and I'm going to basically copy this method for the other condition. So I'm going to define an implicit def inductive implicit def inductive. I'm going to call this GT for greater than. This will take the exact same 5 type arguments, but the implicit instances that I'm going to require are an implicit merge. As a merge of this time, I'm going to have n1 in the original list, so I'm going to say n1 with t1, so that is the original first list, the tail of the second list, and this intermediate result, and the implicit instance of less than as the type n2 less than n1. So if n2 is less than n1, then n2 needs to stay in the final result. So I'm going to return a merge where the original lists that I'm going to merge are n1 with t1, n2 with t2, and n2 prepended to the intermediate result. And as an implementation, I'm going to simply instantiate this type with no implementation. Now, these two methods are pretty hard to read, but if you keep very careful, close attention to the types, they will tell you everything. So I'm going to go through the first example again, and the second example is very similar. So inductive LTE works in the following way. If the compiler can find an instance of merge where the types are T1 and the original second list, and the result type is IR, and the compiler can also find that n1 is less than n2 through an implicit instance of less than or equal, which we created in part 1, then the compiler can automatically build a merge where the first list merges with the second list, and the result is going to be n1 prepended to this original intermediate result. And the second example is going to be very much the same. Now, let's go ahead and add an apply method to merge. So I'm going to define an apply, which takes 3 type arguments, which I'm going to copy from the merge definition because they are the same. And given an implicit instance that I'm going to call merge that has the type arguments LA, LB, and L, then I'm going to simply return that merge instance. So this acts like implicitly if you want. So at this point, we should be able to test this merge operation. So let's go ahead and define let's call this valid merge. And I'm going to define that as merge of, and I'm going to pass 2 sorted lists. So I'm going to say _1 with _3 with h_nil, for example. And let's say _2 with _4 h_nil, so that they intermingle. And the end result should be 1 with 2 with 3 and with 4, and finally with h_nil. And I'm going to simply say merge.apply. And if you explore the implicit hints, you will know the steps that the compiler will do. So we have inductive LTE, inductive GT, inductive LTE, and then basic left. And these inductive steps are for the comparison types, which are also based on implicits. So basically, between the apply sign and basic left, this is what the compiler does to figure out the creation of the merge instances. So in other words, the compiler does the following operations. It will require an implicit merge of this type. So require implicit merge of this type. And for that, it will run inductive LTE. And inductive LTE will take n1, which is _1, which is less than _2. So it will run inductive LTE and require an implicit merge where the _3 with 2 and 4 and h_nil result in the intermediate result. So I'm going to require an implicit merge, and I'm going to copy most of this type. So it will require implicit merge where the first tail with the second list must result in this _2, _3, _4 h_nil. So it will require this merge. First, it will run inductive GT this time around because 3 is bigger than 2, and require an implicit merge. And in this case, we will take the number 2 out. So I'm going to add the types here and remove what's not necessary. So we will require an implicit merge between 3 h_nil, 4 h_nil, and the intermediate result is going to be 3 and 4. So this is the expected result. Now, in order to do that, it will run inductive LTE again and require an implicit merge. And because 3 is less than 4, it will run the inductive LT, and the intermediate result is going to be a merge of h-nil, 4 h-nil, and 4 with h-nil, which it can find by running the basic, I think it's basic left, because the h-nil comes first. So it run basic left with the list underscore 4 with h-nil. And so because it can run basic left with this type, it will create this implicit merge, which it can inform the creation of this implicit merge, which will inform the creation of this upper implicit merge, and finally it will inform the final merge that we are requesting at merge.apply. So this is the sequence of operations that the compiler will perform. So that was merging, and finally we are ready to go to sorting, and I'm expecting that you are probably way ahead of my writing here. So we are going to do the sorting following the exact same pattern. We're going to encode that as a type. So I'm going to define a trait called sort, and this takes 2 type arguments. I'm going to call this L, which is an hlist, and a output list, which is hlist as well. And if the compiler can find an implicit instance of this sort, it means that a list L can be sorted into the list O. So this is the representation of a sort operation. Obviously, we're going to follow the same pattern, and in the companion object of sort, I'm going to define the axioms of sorting. And we will define 2 implicit basic axioms of sorting. So we are going to sort the empty list and the list of one element, and we are going to write a single inductive sorting axiom. So I'm going to start with an implicit val, then I'm going to call basic nil, which will sort an empty list into an empty list. So this will be a sort of h nil and h nil, and this will be a new sort with h nil and h nil, with no need for an implementation. So this is the starting point, and we make this available to the compiler by default. Now I'm going to define an implicit val, then I'm going to call basic 1. That will take a type argument. I'm going to call n as a natural, and this will be an implicit def. So this takes the type argument n, which is a natural, and this will create a sort of a list that contains just this number n. So this will be n prepended to h nil, and the output list is going to be n prepended to h nil as well. So the list will be able to sort into itself. So I'm going to define a new sort with these 2 type arguments. So I'm going to simply paste them and open and close curly braces because this is a trait. Good, so we have the basic axioms. Now the implicit def inductive is going to require a lot of type arguments. So I'm going to add the following type arguments. And this time I'm going to write the type arguments in a little bit of a different fashion so that it makes sense which type arguments mean what. So I'm going to start with a type argument I, the input list, which is an h list. And this will require an implicit, and this will be an implicit argument list. So I'm going to require more than one implicit argument, and the first thing that I'm going to ask for is a split into 2 further lists. So I'm going to add implicit split as a split between the input list and 2 lists that I'm going to call L and R, the left and right. So I'm going to add these as type arguments here as well. So I'm going to say L, which is h list, R, which is an h list. So now we have the type arguments in place. So we are splitting the input list into the left and right. Now we are going to add more implicit arguments here. So we are asking for the sorting of the L and R. So I'm going to ask for sort, let's call this sort left, as a sort in which the input list is L and the output list is some other list. I'm going to call this sorted L. So I'm going to add this as a type argument here as well. So I have a sort left here. Now I also need sort right as sort with R and some other type argument. I'm going to call this SR. So I'm going to add this in the type argument list as well, which is an H list. So we're splitting the input list into L and R. We're sorting the left into SL and SR, and then we need to merge them. So I'm going to add a merge operation as a merge between SL, SR, and some output argument O. So I'm going to add another type argument here, O, which is an H list as well. So if the compiler can find an implicit instance of split between I and LR, so I is split into left and right, the left and right lists are sorted into S left and S right respectively, and if the compiler can find an implicit merge operation between S left, S right, and this output type O, then the compiler can automatically construct a sort operation between list input I and list output O as, and I'm going to put an equal sign here, new sort of I and O with no implementation here. So this pretty complicated method can be read as follows. Given a split of the input list into L and R, given the sort operation of L into SL, given the sort operation of R into SR, and given the existence of a merge operation between S left, S right, and this output list O, then the compiler can automatically build an instance of sort of I and O. So with a little bit of practice, this kind of method or this kind of implicit requirements can be read pretty much like natural language, all right? So split, sort left, sort right, and merge, all right? So this is basically the algorithm, and at the very end, I'm going to stick an apply method here. So I'm going to define an apply, which takes two type arguments which are the same as the definition for sort, and this requires an implicit sort as a sort with this L and O. And on the right hand side of the equal sign, I'm going to simply return this sort instance. So again, much like the other operations, we're simply fetching out whatever implicit the compiler has access to, much like the implicitly method. All right. Good, so we should be free to test. So I'm going to define, let's call this valid sort, as sort with the following type. I'm going to add an unordered list, so _4, _3, _5, _1, and _2. So we have all the numbers between 1 to 5, and of course h nil. And we need the sorted type as well. So I need to put _1, _2, 3, 4, and 5, and hopefully the code should now compile. So if I put h nil here, notice what the compiler does. And if you click on all of these inductive operations, notice that the compiler will do quite a lot of stuff. So we have inductive, 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 and a whole lot of chains here so that the compiler can find the appropriate instances for us. And I'm going to simply say sort.apply, or I can type that with the right type, and I'm going to say sort.apply. So this will basically move the type hints here. Conversely, if I try to copy this line and paste it here, and I have an unsorted list, for example, 1, 2, let's say 4, 3, 5, the compiler will not be able to find an implicit instance for us. IntelliJ doesn't highlight my code quite right, but I'm going to hit on build and then recompile, and we should not be able to find the right instance here. So we have, actually, let's call this invalid sort so that the naming collision doesn't take place anymore, and we should not be able to find an implicit sort instance. All right, so we have ambiguous implicit values because the compiler will try to find the implicit instance of this type, and it has an implicit collision. And finally, you will get a could not find implicit value for parameter sort, and you will not find the right instance for this type. So this code will not compile. The code will only compile if the types are in correspondence. And correspondence means that the compiler can find the right implicit for your type. So the Scala compiler is pretty awesome because it validates the proof that the sorted list 43512 is 1, 2, 3, 4, 5 and no other list. All right, so the Scala compiler is pretty awesome. But we can make the compiler even more awesome. So what we've done here is just asking for the compiler to validate whether sorting 4, 3, 5, 1, 2 results in 1, 2, 3, 4, 5. We can even go further and make the compiler figure that out by itself. And for this, we will use a trick that we used in the part 2 of this mini-series when we made the compiler figure out what the sum of two numbers was supposed to be. So if you go at the top of your code, if you go to the sum trait here, we notice that the result was stored as a type member and not as a type argument. So this is what we're going to do here as well. So instead of having the result type as a type argument, I'm going to add that as a type member. So I'm going to have type result, which is a subtype of HList. Now, notice our code doesn't compile, and that is for us to fix. And I'm going to fix that by creating a type alias, and I'm going to call sorted, or sort operation, that takes two type arguments, L, which is an HList, and O, which is an HList. So exactly the kind of type structure that we had earlier, and I'm going to have this as sort with L, where the type result is O. So this is the type alias that we are going to use in all these inductive and basic axioms. And the reason why is because when you want to print what the sorted list of 43512 is supposed to be, you're going to see this result in the console, and we're going to demonstrate that shortly. So I'm going to use this sort op type instead of the original sort type. So I'm going to change that everywhere in the method signatures to return a sort op, and instead of sort op being instantiated on the right hand side of the equal sign, which is pretty much impossible, you can't really instantiate type aliases by themselves, you can only instantiate regular traits and classes. So I'm going to have, for example, in the basic nil, I'm going to return a new sort with the only type argument hnil. This is the original list, but I need the type member. So the type member result is going to be hnil. So this is the basic nil axiom, which returns a sort op where the input type is nil and the output type is nil as well. And the right hand side, the actual implementation, is going to be a new sort instance where the type result is going to be nil. And we're going to follow the same pattern for both of these other methods. So here we are returning a sort op with n with nil and n with nil, and we are going to, on the right hand side, return a sort with a single type argument, n with hnil, where the type result is n with nil. All right, so I'm going to put this on another line so you might read it better. And in the inductive method, we are returning a sort op with I and O, and I'm going to simply return a sort with the only type argument I, where the type result is O, which has automatically been figured by the compiler. Now, we have two compiler errors because we're using the sort type. We need to use the sort op type. Now, in order for us to use the apply method correctly so that we can actually see what type the compiler has inferred, I'm going to need to remove the second type argument because sort takes only one, and so I'm going to remove the type argument O. But I'm going to resort to a little trick. The apply method will return a sort op whose type arguments are L, the input list, and the output type is going to be sort.result, because you can use type members in the return types of methods. And I'm going to simply return the same instance because these two types are in accordance. All right, so sort op with L and sort result is the same type as sort L, all right, at all times. And at this point, we can use the sort.apply method by removing the second type argument here. So I'm going to remove that. And if you go to build and then call recompile, the code should compile just fine as it did earlier. Now, the only trouble is that you can't really see what type member this valid sort value will take. And in order for us to do that, we will simply call the show method at the very top of the code that I presented in at the beginning of this video and at the beginning of the series. And I'm going to simply print line, and I'm going to copy this, and I'm going to call show of this value. So sort will be applied, so I'm going to call sort.apply with the type argument that signifies the list 43512. And at this point, I'm ready to actually run this application, and we should be seeing the type tag which stores the result of this computation. So we have a type tag which stores the entire type signature of this particular value, and the type tag is a sort with the list successor 0, so that's _4, _3, _5, _1, and _2, and h-nil, where the type result is, and this is where the magic lies, you have successor of 0, that's 1, successor of 0, that's 2, 3, 4, and 5, and then finally h-nil. So the result type was automatically computed by the compiler to be 1, 2, 3, 4, and 5. So this, my friends, is probably the slowest merge sort ever written, but it's probably the most badass still because it's being done by the compiler before your code is even run. This is pretty awesome. Alright, so this was pretty tough. If you followed along so far, I really appreciate it. I hope this was useful because these skills that you practice in this mini-series are really hard to get. Even if nobody in their right mind would want to do sorting this way, this kind of compiler manipulation is very useful in practice in libraries like shapeless or refined types, so this will have practical utility, and this will help you become a badass Scala programmer, which is my goal. So click that like button for me and subscribe for more videos like this, and follow Rock the JVM on Twitter and LinkedIn for updates on the latest and greatest. I've just released fresh new material for cats, so check out the Rock the JVM website as well. And in the meantime, my name is Daniel, and I'm looking forward to seeing you soon.